go ahead and close everything up and focus up here for a second. I want to get you doing kind of an intro on something, and then I don't know how long this will take. We'll see. It may not take that long. But this is big. This is one of our first really big things we do in calculus. This is one of the two. It's not the biggest, but it's a pretty big one. This is one of the big applications of differential calculus that we can apply to other stuff, physics, and not just physics. I mean, this could be applied to economics or lots of things. Okay, so related rates. Let's just start off with a problem, and we're going to talk through this problem. And as a kind of based on the process that we develop, we're going to turn that into a general procedure for solving any problem like this, which we call a related rates problem. So let's take this example that I've given you on the handout. Okay, so what's this mean, first of all? Gas is being forced into a spherical balloon at a rate of 400 cubic feet per minute. First of all, what's that telling us? I mean, what's the 400 cubic feet per minute? That's weird. I mean, you're right, it's going to end up being a rate. It's a rate, which means it's got to be a derivative eventually. Before we get into the calculus, just describe the situation. It's good to have kind of a mental picture of what's going on. What is that? That's a measure of what? Look at the units. Volume per minute, right? So every minute we've got some kind of a big cylinder of gas that's we're going to open up, and that's how much volume is going to flow into the balloon every minute. Right? That's the rate at which its volume is entering the balloon. So the balloon's expanding, right? So I gave you, here's just some geometry. I mean, you already knew that, I'm sure, but gave you volumes and formulas for volume and surface area of a sphere. At what rate is the radius growing when the radius is 10 feet? What's that asking for? When the radius is 10 feet, it's pretty clear. It's a big balloon, like a weather balloon or something, right? So when the radius is 10 feet, they're asking for the rate at which the radius is growing. What's that mean? Well, what do you expect? What would the units be? Feet per minute. Yeah, it would be, because we're measuring, evidently in this problem, we're measuring distances, lineal distances in terms of feet, right? So then areas would be square feet, volumes would be cubic feet, etc. And time is, we're measuring time in minutes, because you got to be consistent, right? Now, you got to put yourself in kind of a calculus state of mind here a little bit. Let's use an analogy, something that we can all relate to very easily. We talked about this a million times. The trip to Hermiston, right? Where our average, we go 30 miles in 30 minutes. Our average speed is 30 miles per hour, right? But in terms of calculus, our instantaneous speed could vary quite a bit. Let's just say that we were to, we cleared all the roads, and for the sake of an experiment, we're just going to start at 0 and gradually increase our speed over the entire trip until when we get there we're going 120. We're actually going 120, right? And so that gives us an average of 60. We're only, in that case, it's kind of similar to this because the balloon is only increasing its volume the whole time. At any given point in that process, there's going to be an instant where we're going, for example, 50 miles per hour or 80 miles per hour, right? But it's only going to be for an instant, right? But at that one instant, that's what our speedometer would read, right? If we looked at a graph of our trip would look like this. Well, you tell me. Actually, no, I'll tell you this stuff. You tell me. What's it going to be if I want to make a graph of position or distance? Same thing for us. If we're going in just one direction, let's say we're just going to go on the freeway, 30 miles. So it's safe. Go 120. I'm not saying that is, but what would my graph look like then? What are my axes going to be? Position and time, which one goes where?
Time on the X.
Good, okay, and then it's always pretty much going to be that way in physics, isn't it? Because systems change with time, right? And then up here is going to be distance or position, we'll just call it D. And if I'm increasing my speed at a constant rate, what's that going to look like? I've seen some people, you tell me, is this right or wrong, first of all? That's wrong, isn't it? Because what's that saying? The speed is constant, right? Because speed, or velocity, we should say, is the derivative of position time graph. That's a constant, the derivative is the slope, and that's a constant slope. What would this one correspond to? This picture would be different. What would the story be for this picture? Start at some speed, 60 in this case, and just go 60 the whole time, right? We pass the starting line going 60 with our cruise control on, and we travel that speed the whole time, right? Okay, so ours is going to look different. That would be cruise control. What's ours going to be? Okay, well, yeah, so I think, is that what you're saying? Something like, I mean, I probably didn't draw that right, but you get the idea, right? That's us, right? Because we're constant acceleration the whole way. So at any instant in time, so at this time right there, call it T1, how are we going to figure out what our speed is? Derivative. And what's that going to give us relative to that curve? The slope of the curve, which we could easily draw by drawing a tangent line. This would be the slope of the tangent to the curve. It's the same thing as the slope of the curve, right? Make sense? Okay, so we're doing the same kind of thing here, only we're doing the same kind of thing. Our graph, instead of being position or distance versus time, what's it going to be? Volume versus time, right? Does that make sense? Okay. All right, so now what? So we're going to, first step is always going to be, we're going to define, we think of this as always in calculus. Calculus is dynamic, it's changing. So it can't just be a picture, it's going to have to be a movie, right? And each frame in the movie, so it's each frame in the movie is going to be an instant in time. In our frame speed, it's not just won't be 60 frames per second, it's infinite frames per second, right? But we're going to pick one frame in for every. Wow. That's so anyway, so each instant in time is going to correspond to a frame in our video, right? So then, can we hear this? Talk really loud, exactly, yeah. So in the frame, so we want to be able to identify for a given snapshot, and I call these things, you'll see, you don't have to look at this now, but I'm going to refer to these as snapshot variables, because they're going to be one frame in our video, right? What are we looking for? What's the frame we're interested in? Right there, that's the one we want, right? So this identifies, this is the frame we're interested in. That's a dangling participle, sorry about that. I should say in which we're interested, sorry, English types. So that's, in other words, that's our snapshot. So what are our snapshot variables then? Well, there's one of them, isn't it? Snapshot variables are R equals 10, right? And we're, feet, but we know our units aren't going to change. We're just going to make sure we're using standard units. And whatever they are will go up and our answer will be in the appropriate units. What else do we know? We know V? Oh, hold it, but that's not V. You guys told me that was something different. You actually said the right word, too. It's a rate of change, right? So, yeah, it's a rate of change of volume. Okay, so now think about that in terms of what the calculus quantity would be that goes with that. What's that going to be? It's not V. It's dV, V dt. Good, and the reason we know that is because the units give it away. right? You look at the units, and if it's units of volume over units of time, then that has to be dV dt, because it's change in volume over change in time, right? So the units are a giveaway. So then we also know that dV dt equals, I'm going to put a space there for a second, you'll see why, positive 400. Okay, now that's, a lot of times we would call this like a V prime, right? Because we don't want to write dV dt, that looks cumbersome, to have all those ratios in there. It just looks, looks too busy. We want to make it look as simple as possible. But we're going to add another little element here. In physics especially, whenever we talk about rates which are with respect to time, because they're so common. I mean, almost everything we do, we're looking once again at a system that changes with time. Not always. Like if we're looking at, if we want to talk about the relationship between, pressure and volume or something, maybe we'll end up doing like dV dP or something, and that's different. Then we call that V prime or dV dP. But most of the time, a system evolves with time, and we're interested in how the system evolves. Because it's so ubiquitous, we would write this instead of a prime as a dot. When we put a dot instead of a prime, it means the derivative specifically with respect to time. So what if it's a second derivative with respect to time? Two dots. It would just look like two dots lined up horizontally, okay? And we don't really ever need to go more than that, typically. We've never done an example in calculus where we do more than that. Because, think about, it's at some point it becomes counterintuitive. Like take kinematics. If you start with position, V dot, or X dot would be V, right? And X is position. X double dot would be A. And beyond that, what is there to go to? Nothing that's really useful to us, right? So we get V dot equals 400, and then that's all we're given, but just as important, what are we trying to find? Okay, and what's the rate going to be? Of R with respect to T. There you go. So we're looking for dr dt, which we're not going to write that way anymore. We'll just write it as R dot equals what? Okay? So there's kind of our list of what we're given, including rates, and what we're trying to find. Presumably a rate, too. Okay, but not always. But if we weren't trying to find a rate, we wouldn't need any calculus, right? Well, is that true? I don't think that's a true statement. But most of the time we're looking for a rate. Now I got to try to build a problem where we don't need calculus and we've got to find a non-rate. Okay, well. Anyway, there's step one. Okay, step two. Step two is we want to come up with the parent equation. And in calculus, when we talk about a parent equation, we mean the non-differential equation. A differential equation is a big fancy word, and in your future there's lots of classes involving solving differential equations, systems of differential equations. But a differential equation is nothing more than an equation that involves one or more derivatives. That's it. That's all it means. So we want to come up with a static equation, something that doesn't have derivatives, so it's not changing, that's going to relate these variables. Okay, so what are all of the static variables? So if we just blur our calculus vision and ignore the rates, what are the static quantities involved? Well, I don't want, and I'm not looking for numbers here. I just want you to tell me, what are the types, what quantities are we talking about here? Volume and? Well, okay, eventually, we'll ignore part B for now. You're right, though. But in this part, volume and? And no, not time, because time is, that's not a static quantity. And, okay, but ignore, let me move part B out of here. Part B we don't need to worry about. Part B we can get rid of. But if I look up here, I've got a rate of change of volume. So when I say blur your calculus vision, ignore the dots.
Great.
I've got V's and radius, not R. R is radius, right? I've got volume and radius are what we're comparing. Do you understand what I say then? That's kind of a dorky way to say it, but when I say blur your calculus vision and ignore the dots, we're ignoring the rates and we're just looking at the static quantities that the rates are relating, right? We're relating volume and radius here, right? So we know those are the property, or those are the quantities that are involved. What is their static relationship? How are volume and radius related? Well, like that, right? So that's our parent equation right there. Okay, so then step 2, all this stuff up here was step 1. Identify the players in this whole related rates problem. Step 2 is the parent equation, so that's going to be V equals 4/3 pi r cubed. What do you think step 3 is?
V dot. The dot.
Good. So we're going to relate the rates by implicitly differentiating with respect to t, right? Does that make sense? Isn't that cool? I mean, to me, that's amazing that we can do that. We can start with this static equation, and then just by doing stuff we practice, by implicitly differentiating with respect to t, we're going to go way beyond what we've been able to do before. And we can relate the rates of change of volume to that of radius. Right? That's huge. So step 3 then looks like this. What do we get if we implicitly differentiate?
Dot.
Call you back in a sec. Bye. Mr. Hagwood. I get calls from Mr. Hagwood every period. So what's this side going to be if I differentiate with respect to t?
V with the dot.
V dot.
V dot.
Good. So here we get V dot. What about over here? I've got this 4/3 pi. I can leave out front, right? What's the derivative of r cubed with respect to t?
3r squared.
So I'm going to get good. 3r squared
R dot.
times r dot. Good. Right? And then the 3 just canceled the 3. Right?
Oh, yeah.
Okay? Okay, so there's the result of doing the calculus. And now the final step is no big deal. The final step is, okay, what are we trying to solve for? Let's isolate that and plug and chug.
Dot.
Right? Yeah, good. So then step 4 is we're going to isolate r dot. So r dot would equal v dot over 4 pi r squared. And now if I plug in the numbers, we get positive 400 over 4 times pi times 10 squared, which is 400 over 400 pi. I heard somebody say that. So 1 over pi, what should our units be? You already told me. Feet per minute. How about that? Isn't that cool? So that tells us exactly at that time when the volume is 400, that is the rate at which the radius is increasing. Just like we could say at some time during our trip to Hermiston, we're going to have a specific speed on the speedometer, right? Same kind of thing. So we could maybe let's go one step further with this. And this is pretty interesting. I mean, this is what calculus and physics does for us. You start to really be able to see the details of the world around you. I mean, like little things. I apologize for this in advance, but you're going to start analyzing little things and looking for explanations why. I may have even mentioned this to you earlier, but we've all maybe had this experience where when you're blowing up a balloon, what happens? What's your experience of blowing up a balloon like?
Disappointing.
I mean, it's disappointing eventually, but at first it's really satisfying. First breath and the balloon just goes like that, right? And then after a while the balloon stops. You keep huffing and puffing when it's out here, and you hardly even see any movement of the balloon, right? Well, why is that? I mean, if we look at volume versus radius, in this function, let me borrow this function back here. We have this guy right here, right? Look at this. This is a pretty interesting equation. We relate these rates like that. So if we're going to look at a graph of V dot versus R dot, well, V dot equals that times R dot, right? See what I'm saying? So if we were going to graph this thing, we actually have to graph, this would be a tough one to do in a way, so how about if we did, let's do this in a different way. Let's do V dot over R dot as a function of R. So this is gonna give us V dot over R dot equals 4 pi R squared. So the ratio of change in volume over change in radius as a function of radius. Okay, so it starts off, I think I had that right.
Wait, is that?
Say it again.
Oh.
No, it's different. Okay, I'm gonna make one more tweak to this, because that's really not what we want. I want to flip this. I want to take the reciprocal of both sides. What I really want is R dot over V dot, right? Because we want to look at how fast is the radius changing with respect to a change in volume, so a breath of air, right? So for every breath of air, how fast is the radius changing, right? So that's going to equal 1 over 4 pi R squared, right? So questions on that? Does that make sense? Right? So that's giving us kind of a gauge of how fast is this, how satisfying is each breath. But what does that function look like for the domain R is greater than 0? 1 times 1 over 4 pi, but the important part is the 1 over, it's proportional to 1 over R squared. Right? What's 1 over R squared look like? Well, as R approaches 0 from the right, let's take a limit. The limit of R dot over V dot as R approaches 0 from the right. Small positive radii would be what? 1 over 0 plus squared is 0 plus. 1 over 0 plus. Positive infinity. What is the limit? Let's try this one. We haven't talked about this yet, but see if you can handle this. Limit of R dot over V dot as R approaches infinity. What's that going to be? 0. Right? And it's nonlinear. So this is just going to look like this, isn't it? It's going to go. So that first breath is pretty satisfying because the rate at which you're blowing up the balloon, the radius is increasing really rapidly. But with time, not so much. Right? That make sense? Next time you're at a kid's birthday party, pull that out and explain to them why they're so disappointed after a while. Yeah. Okay, what about the second one then? So what is the rate at which the surface area is growing when the radius is 10 feet? So same kind of thing, right? Only this time, how would we change, or maybe just add to or delete from our, not delete from, what would we want to add to maybe our step 1 here, our snapshot variables, for part 2? Okay, good. So we could do, yeah, I'm hearing kind of the right things here. So we know what R dot is. We can fill that in, right? R dot's 1 over pi. Okay. R dot's 1 over pi. But what's the new question we're asking? S dot. Okay, so that means a new parent graph, right? Now we need a parent graph that's relating what? What are my static quantities going to be now?
S to R.
S and R. Good. Surface area and radius, right? So we know that one. We know that for step 2 down here, surface area equals 4 pi R squared. And so what do? Okay. Differentiate, right? Relate the rates. Differentiate with respect to time, because we need dots in there, right? We've got to have derivatives with respect to t. So what is this? So there's what we're looking for. What do we get over here?
8 pi R R.
Bingo. Okay. And that's, we know all those things. Plug and chug. 8 times pi times 10 times 1 over pi equals 80 units?
Feet squared.
Yeah, square feet per minute at that time. Did you notice something kind of interesting up here with this related rates problem, or with this related rates equation? What about that? Isn't that interesting? So the rate at which the volume is changing is proportional to the surface area. Wow. Doesn't that make sense though? I mean, think about, that's a couple of your mind, think about where that's coming from. So the rate at which volume is changing is proportional to, regardless of the rate at which, the constant rate at which we're infusing volume. It's got to be proportional to that outer layer, right? That's just, I mean, that's that, you know, that surface of the sphere. There's something pretty revealing in there about just the way geometry works, you know, about three-dimensional geometry. That's a pretty cool equation. All right, make sense? Okay, probably enough for a Friday, right? Okay.
It's not for 80.
What's that?
It's not for 80.
Yeah, well, no. Not on Wednesday, that's different. Wednesday I keep charging on, but if it's a Friday, yes. No, no, it won't be. It's gonna be, no, although we could do something, good question. So what if we took like a cube? I mean, there's gonna be a proportionality for a cube also, because if we take volume for a cube equals x cubed, v dot would equal 3x squared x dot, so there's surface area. It shows up in there too, but it's times 3, right? But I'm sure there'd be somewhere it wouldn't work too, where it wouldn't really show up very conveniently. Like a triangle. A triangle would be tough, because a triangle is going to have multiple, you know, it would never work for that. Because a triangle, think what a triangle, or I mean a triangle, like an equilateral, what do you call that? Regular, yeah, what do they call that? Regular tetragon. If it's got all the faces are equilateral triangles. See, that's going to end up having a formula that's going to end up, it's going to depend on both side length and height. And you have to solve height in terms of side length, it's going to give you a sum. So you end up with multiple terms in that, so it won't work. Yeah, but it works in some cases. Yeah, it works. Yeah, it works in some cases, but not all. You have to think about why that is. What would be the patterns? That's a very good question, though.
All the same.
Yeah.